Alright, so we're going to talk about uncertainty principle today. And uncertainty principle was first devised by Werner Heisenberg, and that's why you hear it as Heisenberg's uncertainty principle.
Yeah.
But usually you can just call it uncertainty principle, and it's implied. One of the statements from Werner Heisenberg about uncertainty principle is one can never know with perfect accuracy both of those two important factors which determine the movement of one of the smallest particles, its position and its velocity. It does not mean that I can find out the position of certain object, microscopic object, at 10 seconds. And after 20 seconds, I can find the momentum of the same particle, and then I can be perfectly accurate. That's not what it means. It means simultaneously, at the same instant. So, when you talk about uncertainty principle, it has to be both at the same time. Okay? That's what Heisenberg's principle in short notes says, and we'll go into detail about what the equation means and all that. Any questions so far?
Not yet.
Not yet. Okay. This principle has been around for quite a while now. I think it was developed in 1925. So that's more than 85 years now. And it's one of the basic building blocks of quantum mechanics. So basically, uncertainty principle gives an advice to us saying that you can't have perfect knowledge about something that you really want to know in the atomic world. So if you have this quest for I'm going to do measurement for hundreds of times, millions of times, nature will stop you from doing it. Okay, that's what it means. Now, where do you see these effects? You see these effects in microscopic world. So the smaller the object gets, the bigger the effect of uncertainty principle. The larger the object, like a chalk, I can see the position, I can find the velocity, momentum easily. It's pretty simple. It's a classical system. That's all. Now, if you divide this into a billion parts and keep going into atomic scale, that's when you look at it, you can tell, oh, is it that or this? That's when it gets sketchy. So how does uncertainty principle work? Uncertainty principle works basically with canonical conjugate variables. Now, what does it mean? I can't use uncertainty principle using some arbitrary variables and say, hey, I can determine this effect and this effect simultaneously at the same time, so I've defined uncertainty principle. That's not what it means. Uncertainty principle has to do with canonical conjugate variables. Now, what does it mean? Let me give you an example. In math, when you take a Fourier transform of one variable and go into the basis of another Fourier transform, these two things are canonical conjugate variables. For example, position and momentum are canonical conjugate variables. Okay? Energy and time are the same thing. That means you can take a Fourier transform of energy and go into basis of time, and you can take Fourier transform of x and go into basis of momentum. And only between these two objects you can define uncertainty principle. I can't define uncertainty principle between the momentum and the energy. These are non-canonical conjugate variables. So once in a while you see philosophers talking about uncertainty principle, in your coffee break or something like that. For a physicist, it does not make sense because it has no basis. Okay? Any questions?
So there's no connection between momentum and that?
No, there is connection, but they're just not canonically conjugate variables. It means that you cannot have Fourier transform between this one and this one. For instance,
Sorry, just Fourier transform?
Yeah, just Fourier transforms. For instance, let's say this is a function of momentum, right?
Uh-huh.
You can do an integration from negative infinity to infinity e to the power negative k x dt. And your momentum, I believe, is that, and you can change this into space. Okay? This is what it means. So basically, you can transform from this integration to this integration by doing Fourier transform. But in momentum and energy, you can't do it.
Okay, there's no.
There's no. Yeah, it has to do with topological sets, and you have to go into gory math detail.
Then it's not continuous transform.
It's not continuously transformed.
Okay.
Yeah. And then the basic mathematical foundation, you have to, it's another whole different class.
Okay, got it.
Yeah, we're not gonna go through it. So in terms of momentum and position, you write this uncertainty principle. Okay? Our good old equation, everyone loves it, right?
Okay.
So this is
delta
x.
Delta x and delta moment.
Delta moment.
Yeah.
Momentum, not moment. Moment is different again. Okay? So this momentum is again the momentum of x. It can be momentum of y. This way. And this h over here is the Planck's constant.
Yep.
And Planck's constant h is 6.26 times 10 to the negative 34 joules per second. Okay? So you can see how small this is. Negative 34. So, to see its effect, you have to be really small.
Okay.
You have to be a size of an atom to see yourself into, that effect. So that's what uncertainty principle is in momentum and position basis. Okay? And del x is also standard deviation, and del p is also standard deviation of the momentum. That's what it is. Okay. So when you increase the knowledge of your momentum, you decrease the knowledge of your position, and that's what it is.